Okay, in this session we will understand principal component regression. So now I think you are fed up from principal component analysis, then NMF, and then this is again a new topic, principal component regression, which is you can say which is not quite similar to principal component analysis, but still it is a part of PCA itself. Okay. Now from the topic, let me explain you the, if you remember the linear regression, I think you remember, if you remember linear regression, which I think you remember, uh, if I have a data set x1 to let's say this is xm, and based on that I also have some y variable, right? Because it's a combination of x1 y1 x2 y2 and something like that, because it is having some target variable, it is supervised learning, so they have y component, and that's why I have x1 y1, the complete data set, right? uh, so the equation that I am getting from this data set, I am having the y here, and I will having I'm having theta of 0 plus theta of 1 of x plus theta of x of 2, and so on till theta of m xm. This is the equation for linear regression when we are doing our supervised learning and linear regression precisely. But now, as I told you, that because we are using unsupervised learning, and you know that PCA, what PCA do here is it it will never use x1 x2 x3 and so on, but it uses, so let me just write the another term z1 z2 z3 and so on to zn. Okay, why? Because I am reducing certain dimensions. Let me just write z of k here, because you know I'm reducing the dimension here, and I cannot write the x1 x2 x3 and x4, because I'm reducing a dimension from this dataset to this dataset, and we had seen that with this thing. You had seen this, right? So my x of I belongs to uh, 2 dimension. Then with the help of dimension reduction projection, what I'm saying, I'm representing z of I, if you remember, then it belongs to R. So this is in 2 dimension and this is in 1 dimension. So now you can remember that I'm not using x, I'm using z for my principal component analysis. I hope you remember this, and this is the simple linear regression that you did. But however, now in the um, in this principal component regression, the things are going to be a little bit changed, because I'm going to use regression with least square. You know that what is least square, right? The distance between the two data points has to be minimum, and we are squaring that, right? We had seen that minimum square error, mean square error, sorry, that we had seen. So it is a least square here that I'm using here for the regression, for fitting the regression line, right? So for the topic, the topic is, in one video I actually written down principal spelling actually wrong. I written down PLE, but it is PL. Okay, I'm so sorry for that, for those typos. So principal component, and it is not analysis, it is a regression. So PCR instead of A. So now I'll write here that to fitting a regression line, using least square, previously what we are using, so least square, previously what we are using, previously we are trying to use z1, another component is z2 till z of m, and these are the principal component. If you remember, this is the principal component of PCA, and they are, in more general way, they are the new independent variable, right? So I'll simply write here, these are the new variable. Okay, previously we had seen, and based on that, what we can do is I can model it. So where is it? I'm going to model it. I can model it linear model using least square. Linear model using least square, and I will write the equation now. Instead of using x, remember I'm using least square, and that's why I'm using z1, z2, z3, those components, principal component, right? So I'll write theta of 0 plus theta of 1 z of 1 plus theta of 2 z of 2 till the last row of the data set. Okay, this is the linear model that I'm going to use. Okay, so this is the linear model, and these new variable that you are getting over here, this z1, z2, zm, these new variable and or the principal component, they are giving you two possible things. Okay, these principal component that you are getting over here, they are giving you something, and what it gives you, see, so I'll write it down here, these new variable that is the z to zm or principal component, I mean, so sorry for writing like this. This new variable z1 to zm or principal component can help in first thing is it can give you the variability. It gives you the variability in the data. I'll explain you what do you mean by this variability. And the second thing that it gives you is the relationship. Oh, I think I had done some spelling mistake. This is H actually. I'm so sorry. So come on, I don't like this. So I'm going to remove it like this. Now I'm going to be pro in this. So relationship with the response. And when I say response, it is nothing but my y. Okay, so this is the relationship, how your feature is related with the y component or response. Okay, these are the two things that your new variable is going to give you in PCR, principal component regression. And now if I'm saying that if I have a complete set here from z1 to zm, that I'm not going to use this complete set. What exactly I can do is I can take some small subset, like from z1 to z5, and they are the 5 new variable that I'm taking from the space. 5 new variable. So I'm showing you the first point, that how it is related with the thing. So what do you mean by variability? Variability means the complete set that is here, the complete set. I am not going to use that complete set, but instead I can show all the things from these 5 new variable. I don't need, so if my z, so let's say this vector space is like of 100 variable, then I don't need these 100 variable to show the things inside the data set, or any kind of relationship or correlation. I don't need this complete vector space. Instead, I can use these 5 variable only 5 variable from the 100 variable. I'm using this 5 new variables only, and I can show everything that these 100 variable is trying to show you. Exact same thing. So why I'm not going to use these 5 new variable? I'm definitely going to use these 5 new variable if they are giving me the same result. as these 100 variables are giving me. So what I can say here that let me again, I'm changing too much colors over here. So again, 95% of the variability, 95% of the variability between data can be shown, this is 95%, can be shown actually, can be shown with the help of these 5 new variables only, with the help of a bunch of variables. So z1 to z5, only 5 variables. Okay, so this is the first point. So instead of using 100 variable, I can use this 5 new variable. They are giving the same exact, you know, output as these 100 variables are giving me. So this is the first point. And the second point is that these 5 variable are 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 having better relationship with the response variable. Okay, and this is also the assumption that I'm taking over here, that those 100 variables, I don't know how it is related to the y variable, what kind of relationship it possesses, but these 5 variable are having better relationship than that of the 100 new variables, okay, or the 100 variables. So I can simply I can write the second point to explain that. I'll write we hope, or we assume that, we hope that these 5 variable z1 to z5 is having better relationship with response variable y. Okay, so these are the 2 points that we need to cover up. Okay, so I hope you understand the you know, the what you can say, the intuition behind this PCR, and this is the thing that we're gonna understand. So now if I have a original set like from x1 to xp, it is going to be vary, right? It is going to be vary, but instead I'm going to use um, so if I have let me just formulate it again. So if I have x1 x2 x3 till xp, and from that set if I'm using only z1 z2 till zm, okay, these z1 to zm are going to be pretty much more, it will give you more variability, and it will give you precise relationship with the response variable y. Okay, so let me again formulate it with this writing section. This is okay. Let me put it in this way. So if I have a set from x1 x2 till xp, and let's say my p is 1000, okay, then from this set if I am taking only z1 z2 till z of m, and let's say this my m is 5, I think now it is clear. So p is 1000, m is equals to 5, then this set, this complete thing is going to give me all these points. The variation, it give you the best variation or the best variability it will give you, and it will also give you the so I mean I just have to write better variability to mark out the plus point, and the second thing is it will give you the better relationship. I hope you are getting it. It will give you better variability and better relationship. And remember that these m equals to 5 are the new variable that I am taking out from this original variable. Okay, I hope this thing is clear to you. So if p is equals to 1000, and from those 1000 I am taking only 5 new variables, then these 5. So here in this case, these 5 new variables, because of this 5 new variables, right, PCR is going to fit better. Okay, PCR is going to fit better fit better with these 5 new variable as compared to that of these 1000 new variable, oh sorry, original variables. Okay, so I'll write it down here. So if we have P equals to 1000 data point, then PCR will fit sorry, fit just okay, fit our I can't believe this. It's totally I'm writing it just I don't like this. Okay, so fit our okay, least square. This is my least square, and by means of least square, these are least squares z1 to z5. Okay, again the mistake, so curly braces. Okay, so least square, PCR will fit our least square z1 to z5, and it will lead to a better result, to a better result than fitting the original variable, when fitting the original variable. Okay, so this is I want P points. Okay, so x1 to xp, I actually have to write that. So x1 to xp. Okay, so this is important, that I have original variable and some new variable that I am defining from the original variable itself. So my PCR in this case, with the help of these least square z1 to z5, it will going to fit better in compared to that of these original variable x1 to xp. Even though my m, even though I'll just with the oh, even though here here I'm writing, even though my m is basically very smaller than that of p. Okay, still I can but it gives me better result, still gives better result compared to p, still gives better result compared to p. Okay, so m is smaller than equals to p, but still gives me some better result than that of the original point. This is what I want. What other thing that I can conclude here, that I can conclude that, so these m points, so peace line, so these m points are very important feature, are very important, I can say variable, or I can say feature. So important feature, and other variables and other feature and other variable in the case of PCR only. Okay, and the other variable or other feature are simply noise. I can see that. Okay, so these m points here, they are very important features, and compared to the other 95 features are going to simply noise. Okay, so this is the thing with PCR, and to understand it more, let's see the visualization part. Now I'm going to use one graph. The graph, as I think you know that the result of linear regression is in the mean square. We can find it out with the help of mean square error, and so in one axis I'll put that mean square error. So this is the y-axis, and this y-axis says mean square error, or MSE. Okay, so this is your mean square error, and this is the M, and m is equals to 5, you know that. Let me just separate this out a little. This is the separation. Now another thing is so if I have some data points inside this graph, so what is going to be happen is need some colors, different colors here. So this is the line for, let's say this is the line for variance, the maximum information is there, and if my m is equals to 5, then you can say that my bias, okay, so initially bias was very high, it's going to be very noisy earlier, but it comes to 0 somehow. So this is your bias. Okay, this is the graph. So this is your variance, this is bias. I hope you understand. This is going to give you underfit model, this is going to give you overfit model, and your MSE is going to, it looks something like this. It gives you an U-shaped model here. This is your MSE, and what it represent here. This is important to understand, that this complete graph is going to show you. Let me put another color here, and what it says that if you are increasing your m, so let's say my m is like 50, so if you are increasing your m, you get lesser bias model. You can see as you are increasing m, you're getting lesser bias, but if your m is like very decreasing, like here somewhere, so your bias is very high and your variance is small, right? This is also very important. And if your m is somehow here, then you're getting high bias but lower variance. However, when you are getting higher in the m, then you are getting lower bias but high variance. So I will write it down here that as mu increase, so this as mu increase, you get lesser bias model, lesser bias and high variance. And from this whole thing, what will happen is your MSE, that is mean square error, is going to give you the U-shaped. Okay, your MSE is going to be in U-shaped model. This is what we can conclude from this graph. I hope this is a little bit, we can get something from this graph. So m, you already know that these are the new variables that you are getting from the original one. So if my m is like 5, then you can see that it is having a laser bias but high variance, and your MSE, that is mean square error, is going to be in U-shaped model. Okay, so from this again, if P is equals to like 45, that means what is this? So that means these are the original data points, original one, and if my m, let's say my m is it's some values, let's say I'm not putting it over, so this is the asterisk. So these m are least square. Okay, right now p is equals to 45 and m is equals to some numbers. It could be increasing, decreasing according to the data set we're gonna change, and we're gonna see that will happen. So these are the inputs. These are the inputs going to use least square. Going to use least square fit using our original predicators. And what is the original predicator? This p equals to 45, original predicators p. Okay, Now I need to draw some graph here. Now basically the question arises here that how can I choose this m? Well, basically you can take an algorithm again. You can take one algorithm such as cross validation. Cross validation will give you what preferable m that you can use here. So cross validation is the algorithm by which you can take out some value. So k cross validation, leave one out. Those algorithms are useful here to get out some value for the p. Okay, so here I'm going to draw a graph here, again the same graph actually, but we will conclude something from that. So just give me 1 minute for this. This is the graph for MSE and the same separation, but now it is being somehow I have to give some dimension. So this is 0, this is 10, this is 20, 30, 40, 50 and 60. Okay, and let me also provide the variance line. So this is the variance line, and let me also have the bias line here. So I hope you can see this bias line. This is my bias, and for other representation, let's say my U-shaped MSE looks something like this. Just need to redraw it. Okay, this is my MSE. Now if I say that my take the another color, so so that we can differ the things out pretty clear. So now if my 45, this P, this is the I need to clear it out. So this is 45, right? And this is P itself. So if this is the P is equals to 45, then you can see here that my MSE is going to be going to be here somewhere. Here somewhere. This is my MSE point. So this is higher MSE here. Okay. So P is equals to 45. You're getting high MSE. Now let's say from these P equals to 45, you are getting M equals to 22 or like 20, 22 like that. So you're getting lower M, right? With the help of this cross validation, we are getting M is equals to a little bit lower than that of P. So let's say my M is somewhere here in the 23. So this is 23 equals to M. This is my M, and you can see from the graph itself, you can see that the MSE that I'm getting here is pretty much lower for the data point M. So let's say for M equals to 23, I am getting a low MSE. So your M should be, it should be in the middle, in between the dimensions. So it should not be very small, should not be very high. It should be in the between, these two things. Okay, so that this U-shaped MSE, if you are getting more of left, then your MSE is again going to be very high, and if you go more of right, then again your MSE is going to be very high. So you have to be very in between, so that you get the lowest MSE. And this is the thing that you can get from the PCR, principal component regression. And this is the overall PCR, and PCR is not a feature selection method. We are just reducing here the dimensions and not selecting any features. Okay, so we are just reducing. So how we are reducing? Basically, you can see from 45 data point we are taking only 23. Okay, so basically it is not a feature selection algorithm. So I will note it down here, please. here in the node part. So it is not a PCR, is not a feature selection method, we are just reducing the dimensions and not selecting any feature. And now if you have any doubt on the PCR, then you can ask me in the comment section. I'm going to help you in that. Okay, thank you so much for listening.